Okay, so we're recording now. I just share my screen. And I'll go to the notes for the lecture, which I think is this link. Hide the controls that you can't see, and then we're ready to go. Right, okay. So thank you for attending. I feel I should apologize for having a lecture today. The reason is that there was one topic that I needed to fit somewhere into the course, and our timetable is very tight from now on until the end of semester, so I did not see that I could give up today's lecture. So I hope the flexible ways of attending it by Zoom or also watching it on the video as another alternative make up for having a lecture on this day when I know that a lot of people have cancelled teaching for these last 2 days just before the May weekend holiday. Right, so today it's actually going to be a bit of a shorter lecture, so we're going to have a short break in the middle, maybe not the full 15 minutes break. I don't want to keep you too long. I just want to begin by saying what we're going to just reminding you where we are with respect to the course and the arrangements coming up over the following weeks. So next week we will have a lecture in the usual slot, but it's the last of the ordinary lectures before we go into the presentations. But the content of the lecture is going to be a little bit special because I'm going to give you instructions for the student presentations in it. We're going to have some material that we're going to learn. We're going to learn something, so I'm going to teach you something next week as well, but I'm going to do that in the format of giving you example student presentations and telling you how the student presentations are going to be assessed. So instructions for and examples of presentations. So that's on, I guess, the 6th of May. Following that, we go to a non-standard timetable, which I've already announced before, but just to remind you, after that, we're going to follow the timetable, which is on the course webpage. So see timetable on the course webpage. And by now, you should have signed up for a day for student presentations, just in case you haven't. So if you still need to sign up for a presentation, and I've extended the deadline for doing that. Everyone who's signed up already, you can't change what you've already signed up for, so thanks for doing that. But if you still need to sign up for a presentation, I'd like you to do so by the end of next Thursday. So do so by the end of next Thursday. So that's Thursday, the 5th of May. And there's only one date to choose from, and that's the Friday, the 27th of May. So you have to choose. Everybody left needs to take Friday, the 27th of May. So because we're recording, I won't take questions on that now, but when we have the interval, I shall pause the recording and then I'll ask if anyone has questions on presentations. Okay, so today's topic, something that has to be fitted into the course because it's an important area of applied mathematics, and there was no other place to squeeze it in apart from today. So as I say, I hope I apologize for having the lecture today, but I hope the arrangements for being able to watch it at home actually make up for having a lecture today. It is examinable material because this is important material, but there's not going to be very much material today. So as I said, we're going to have a shorter lecture than usual. So everybody knows something about statistics. Statistics are very important in culture. Politicians and other people that want to make cases use statistics all the time, not always in a very, very honest way. But nonetheless, one is used to being told statistics when politicians are trying to convince you that their point of view is right. And you're probably all aware that you have to be very cautious with how you interpret the statistics that politicians tell you. And there are lots of interesting books and videos one can watch about how to lie with statistics that open your eyes to some of the tricks that politicians and newspapers and other institutions use to manipulate statistics and present them in a misleading way. Today, I'm not going to look at that side of statistics at all. I'm going to rather look at the terminology and nature of statistics and also some of the mathematical side of statistics. But just to draw your attention to, it's actually rather an interesting thing to have a look at some of the resources online, or also look at books and try to understand a bit about how statistics are manipulated in everyday life. I almost feel nowadays, so people have talked for years and years and years, decades and decades about how politicians manipulate statistics and use statistics to lie to you. I almost feel nowadays that that's almost like the good old days when politicians used to lie with statistics. Now they just seem, I mean, I'm not saying all politicians, but now there seems to be just more of a prevalence of just blatantly lying without even trying to justify it by statistics. Anyway, this is not a lecture on politics, so let's get to the substance of the lecture. So what is statistics about? Well, as I guess you all have some idea what statistics is about. If we were in a usual lecture setting in the classroom, I would ask for some ideas about this, but instead let's just go quickly through it. So I would say statistics is about analyzing data numerically. So the numerical analysis of data. Now, how do we get data? Well, nowadays, there's lots and lots of data online and lots of online industries. So even the major ones, especially like Google, Twitter, I suppose, has been in the news this week. They all collect statistics about their users, and you use that to train their algorithms so they can target you for adverts and basically make money. So statistics is very important to how they make money. Statistics is also very important in democracy, so trying to understand what the voting population believe about various issues. Or more generally, there's the question of how do companies, for example, that are interested in targeting part of the marketplace, how do they find out about the preferences of their potential customers? So we're going to consider, related to that question, a very pervasive question, so one that occurs in many places in statistics, which is the question, how do we collect data? So statistics is the numerical analysis of data. Where do we get the data from in the first place? So as I said, one way is over the web, and there are algorithms that do that. But suppose we want to survey the population, for example, ask them their opinions. How do we collect data? And one common way of doing that, if we want to survey the population, so for example, I'm not going to be exhaustive of this, we just want to consider some examples of things. So for example, surveys, when one's surveying the opinion of the population, like in what's called an opinion poll in English before an election, where you ask the voting public which way they're likely to vote, so that you've got some indication of how what the outcome of the election is going to be. Obviously, we had the election last week even last Sunday in Slovenia, so it's quite a topical issue. So surveys often we often ask people using questionnaires. I'm surveying the population, and a questionnaire is set of questions that we ask every participant in the survey to respond to the questions. So I want to consider an example. Let's go to, and we've got a lot of space here, but anyway, let's go to a clean page. So I want to consider an example questionnaire just for the sake of discussion in this lecture. So here's an example questionnaire, and it's a made-up questionnaire. I could have used a real world one that I could have found on the web, but anyway, here's an example made-up questionnaire. The sorts of questions, everyone I'm sure will have filled in questionnaires from time to time, been surveyed in one way or the other. And these are the sorts of questions that you might get asked. So every questionnaire somehow has a raison d'etre. That's a reason behind it, a reason for being, which is what fundamentally the people that are interested in getting the answers from the questionnaire, what fundamentally they want to find out. So in this case, the questionnaire is going to be a survey of residents of EU countries so not just one EU country, but the EU countries in general, European Union countries, of the opinions of people on the EU itself. So the idea is that we're going to ask people what they think about the EU. And here is the example survey. Now we're going to have the questions. So the main question is going to be, what is your opinion on the EU? Now, of course, that's a subtle question. People may not have a clear-cut answer to this. So you could give them a line. Hello. Most people are online, or even not. So you could give them a, excuse me, you could give them a line or a set of lines to answer in prose, but that would be very difficult to analyze. So normally survey makers just offer a simple set of options, and you'll all be familiar with this sort of thing. So in this case, you might just have a collection of tick boxes, and you have to tick one of the boxes, and you'd be given a range of possible answers. So your opinion might be allowed to range from very negative to very positive via intermediate states such as just negative I'm just going to write it like this, negative minus VE. That's a sort of mathematical shorthand for negative. Mildly negative, or slightly negative. Let's put mildly. Oops, I've miswritten the I there. So mildly negative. Neutral. I'm a bit worried about space here, but we've got then mildly positive. So this is a shorthand for positive, positive, and very positive. So you'll all be familiar with questionnaires that give you this sort of range of possible answers to a question about what your opinion is on something. You know, it's very hard to answer these questions honestly because, you know, most people will have mixed opinions of one sort or another. They'll see some benefits and some drawbacks of EU membership. Can almost imagine that almost nobody is going to say their opinion of the EU is very positive, because everyone is going to have some reservations about the EU membership. But you could imagine quite a high proportion of people would probably answer that their opinion of the EU is very negative, because when people tend to have negative opinions, they often like to have really negative opinions. So you can imagine the answer to such questionnaires is almost skewed. So that's slanted in one direction rather than balanced, just by the very nature of the questions that are being asked here. Anyway, this is the main question that we want answering, but in order to be able to do something useful with it, we don't just want to know what the answer to this question, but we somehow want to know how it corresponds to other factors that affect the person that's answering the question. So typically, such a questionnaire would contain a question like this, but it would also ask you for some personal data as well, so that it gets some properties of you that it can correlate, that's relate to, and see the relationship between those properties of you and your opinion on the EU. So for example, in this case, so this is a survey of residents of EU countries of their opinions on the EU. So one important aspect of the survey is the country of residence. So which is one of the EU countries, just to be qualified to answer this survey. But it might be interesting as well what the nationality of the answer is, so of the person giving the answer, not just their country of residence. So for example, my country of residence is Slovenia, but my nationality is, well, it's not an EU nationality, but nonetheless, I live in an EU country, but I have now a non-EU nationality, which is British. So we might also ask the nationality. It's always interesting to see if opinions are related to the age of the person that's answering. And something else might be that's relevant. It would be, say, the annual income of the person, to see whether more affluent, that's more wealthy people answer differently on the whole from less wealthy people. So country of residence, that's one of the EU countries. Nationality, that's one of the countries in the world. Age, that's an integer, so this is we'll ask for this in years. Don't need it totally accurately. Sometimes you might have a range of age brackets here. So are you in your 20s, 30s, 40s, 50s, or 60s, or something like that? And the annual income, we'll ask for that. Well, it's an EU survey. Not all countries have the euro, but to standardize it, we might as well ask for it in euros. Okay, so it's very easy to design such a questionnaire. One could discuss whether it's a good questionnaire or not. It's rather similar to questionnaires that were very common in the United Kingdom in the year 2016, when we had our referendum for that in the end decided by a very small majority to exit the EU, which has caused no amount of havoc havoc is chaos in Britain since then. So anyway, so such questionnaires really existed, or very similar ones in Britain in 2016. And this simple questionnaire illustrates several points that I want to raise. So illustrate several points. Or raises several questions would be a better way of putting it. So the first thing I want to talk about is, well, it's all very well to design such a questionnaire, but how do we actually go about using it in practice? So how do we gather the data? We can say to people, answer this questionnaire, but how do we do that? So what we can't do is we can't simply ask everybody who's a resident of the EU to answer the questionnaire, because that's an absolutely enormous population, and it would be a huge, huge job to do that. And of course, many people wouldn't answer the questionnaire anyway. So it's infeasible to ask. So the collection of people that we're interested in their opinions of, that's all residents of EU countries, that's called the population that we're surveying. And so we're interested in a very large population. Let's just call it, like, to make it easier to write, huge population. We are interested in a huge population. So the population is the people we are surveying. So in this case, it's all EU residents, all residents of EU countries, residents. So it's infeasible, it's impossible to survey the whole population. So it's impossible to survey them all. Be interesting to know how large this population is. It's going to be hundreds of millions, maybe even 1,000 million, but probably hundreds of millions, I would guess. That's 1,000 million would be a billion. So instead of surveying the whole population, we do the only thing we can do, which is we survey some of the population, but not everybody in the population. So instead, and in statistics, the words population and in statistics, the words population and sample have special meanings. So the population is everyone whose opinion we're interested in, and the sample are is the collection of people from whom we collect the data. So we're instead going to survey a sample of the population. So these are two important words in statistics: sample and population. So I want to just ask some of the people their opinions. And the idea is then we can't ask everybody, but we're going to say, well, as long as the sample we look at is reasonably representative of the population, then we can use results from the sample itself to infer results about the population as a whole. So if like 90% of the sample say that they're happy with the EU, that they have a positive opinion of the EU, which would certainly not happen, but if they did say then if our sample were representative of the whole population, we would infer that somewhere around 90% of the whole population of the EU had a positive opinion of the EU. Of course, that statistic is completely made up, but the important is the idea that we want the sample to be representative of the population, in that when we get a result about the sample, we've got good reason to believe that that result applies to the population as a whole. So we want a sample that is representative of the population. So results about the sample can be used to infer results about the population as a whole. Another way of saying this is it avoids bias. So we don't just want to survey professional men in their 40s or something like that. Then we would get one opinion, the opinion of professional men in their 40s, but that's very unlikely to be representative of the whole population. We want to get a good spread of people from the population in our sample. So we want it to be representative of the population, and this can be achieved by the best way of doing it is by choosing the sample randomly. So if we've got some way of randomly selecting, say, some number of thousand of people from this population of EU residents, then if we select the people randomly, if we select enough people randomly, then the randomness ensures that that sample is quite representative of the population. So this is achieved by choosing the sample randomly. So continuing these bullet points, I should have really broken the page. So we also want the sample to be large enough that we can trust the result. So if we just asked 100 people, that would not be large enough to get a very meaningful result. But not too large, because if it's too large, then it becomes infeasible and also very expensive to run the survey. So not too large. We want running the survey and processing the results to be, whoops, sorry, that's supposed to be and processing the results to be feasible So feasible means we can do it, we can actually carry it out. Feasible and economic. We don't want it to be very, very expensive to run the survey. Okay, so those are some issues. These are all major. These are all really major issues about running a survey, and one could go into all of them in quite a lot of detail. But as I said, I want to be quite quick today. I don't want to spend too long on today's lecture. We haven't got to the maths yet. Before getting to the maths, I want to talk about one other very important factor that's related to that particular survey, that it illustrates three different kinds of data that we might have. Then we'll have a short break, and then we'll start again with the mathematical part of the lecture today. So that survey we've already got illustrates 3 different kinds of data, and this is part of the important material. This is part of the material I want to cover today, these 3 kinds of data that one gets in statistics. So the survey illustrates the 3 kinds of data, the three main kinds of data in statistics. And these are numerical data, so numerical data is when the data is when the data is either a number, so it's either a real number or an integer. So the answer is either a real number and examples of numerical data here are from our survey are age. Well, the 2 instances of numerical data are age and income. Those are both numbers. In this case, they can both be integers, so age in years and income in euros, which we don't want. We're not interested in the cents there. So these can both be represented by integers, but in general, numerical data is either discrete, that's an integer. So we distinguish between discrete numerical data and continuous numerical data. We call numerical data. So in this case, we've got discrete numerical data in our survey, but we might, for other situations that we're gathering data, we might have continuous values. That's continuous value means when we're asking for a number that's a real number. So that's called continuous data. So in our survey, we just had discrete data. So the other main kind of data is categorical data. So I said 3 kinds, but categorical data we're going to divide into 2 categories, into 2 subcategories. So in categorical data, the point is we only have a few fixed possible answers. So only a few fixed possible answers or possible values for the data. So for example, country of residence, that's an EU country. So e.g., so I should put here, for example, so for example, country of residence, that's one of the however many EU countries there are. I don't know how many there are. So country of residence, nationality. Nationality is one of the countries in the world. And another example of categorical data is the opinion of the EU, where there were exactly 7 possible answers, ranging from very negative to very positive. So there were the 7 different possible answers of this. And these subdivide, this kind of categorical data, we can subdivide into 2 subcategories. So we divide these into what's called nominal data. And this means there is no ordering between the categories. There's no ordering on data. So for example, the country of residence, there's no order on countries in the EU and nor on countries in the world. I mean, one can order them in various ways, for example, by gross domestic product, GDP, or something like that. But the countries themselves are not, there's no natural ordering on the countries themselves. So e.g. countries, as opposed to what's called ordinal data. When you have ordinal data, there is an ordering. So, for example, the main one here, the opinion of the EU. So there are only 7 possible answers. There's an obvious ordering on them. There's the answer very negative, then the next one up in the order is negative, then mildly negative, then neutral, then mildly positive, and so on. So there's an obvious ordering on the data there. So I think I'm going to remove the 3 here because it's a bit confusing. I'm just going to say the main kinds of data. The data are numerical data and categorical data, and categorical data include nominal data and ordinal data. But numerical data is also considered ordinal data because numbers have an order on them. So I should put that at the bottom of, let's put it at the side, and so I'll just put a little parenthetical remark. Numerical data is also ordinal data because it has an ordering on it. Okay, so what I'm going to do now is I'm going to pause the recording. I need to stop sharing screen first, and before I do that, I need, oh, hang on. Right, I'm going to pause the recording. So I think we'll have a break until 1:10, but before we have the break, I mean, well, or while we have the break, does anyone have questions about presentations or anything about that? Because this now would be a good time to discuss it. So you're not being recorded, so feel free to ask a question if you want to. You can also ask questions in the chat. Right, well, if there are no questions, you can think about if you want to ask questions. You're welcome to ask a question in the chat. I'm just going to get... So recording's still on, is it? Oh, it seems to be. Okay, so welcome back. Just check my... can somebody just confirm that you can hear me? Sorry, I'm having problems with my Zoom controls. Okay, so the second part of the lecture, I want to do the mathematical side. It's not going to be very mathematical. We're going to talk about the mathematical quantities that are the most common ones that are used in statistics. So, so one of the most important things is a notion of statistic called summary statistics. So what summary statistics are, they are values that capture some important property of the data. So they summarize a property of the data. So values that capture a property, well, let's say properties of the data. Properties. I'm sorry about my writing, but my tablet response on my computer is rather slow, and sometimes things come out a bit messily, and I don't want to spend all the time correcting it always, but I'll try to slow down my writing speed so that it writes more neatly. So we want to summarize properties of the data, and one of the most familiar of these are the summary statistics called averages. And I guess you all know what an average is. As you probably know from high school or other school, there are different kinds of average. And what they do, what the different kinds of averages share in common is that they all measure, so these summarize either the property that you might call the typical value. So the average is sort of the typical value that one might expect of data, or sometimes it's also called the location of the data, where one expects to, if you measure a random person, where one expects to find the value, or it's sometimes also called the central tendency. So these are all words for describing the property that's summarized by an average. But essentially think about it as an average is a quantity, a statistical quantity that will represent a typical value of the data. But these are different ways that one finds it described, what it's doing. So averages are important. You know, this is the average salary of a Slovene person or something like that. Then it's you know, it's a very important statistic about the country. Another summary, so another property that one wants to summarize is not just the typical value, but how much variation there is between the different values that one can get. So these we can call these measures of spread. How much spread, that's variation, how much do values differ from each other? Spread or dispersion is another word that's used in this case. Dispersion, you talk about a crowd dispersing. For example, if you have a crowd of protesters and the police fire tear gas at the crowd, then the crowd might disperse. That's run off in all different directions. So here we're talking about, so there the crowd is increasing the distance between people, and dispersion in this case is how spread apart are the values of the data. That's this use of dispersion. So measures of spread or dispersion in the data, which measure essentially the amount of variation in the data. Variation, the size of the variation in the data. So we're going to look at some different averages and one important notion of spread, which is the most famous one, which is called the standard deviation. So let's look at averages first. And you might remember from school that there are essentially three main averages that are considered. So averages. So suppose we have n items of data. So n is some natural number. So suppose we have n items of data. Let's call them x1 up to x sub n. Statisticians often use capital letters here, so I am. So the most common form of average, and actually if you use in English the word average and you don't qualify it in any other way, you often just mean this common form of average, is what's called the mean, or more precisely the arithmetic mean, or mispronounced that. Arithmetic is the noun, this is the adjective, the arithmetic mean. So when you have the adjective, you put the emphasis on the E in arithmetic. So the arithmetic mean, so this is like a typical value of the data. And as you all know, I guess, you simply sum the n values and divide by n to find what's called the typical value. And often this is represented by the Greek letter mu. So this is a Greek letter mu, or statisticians also write x with a bar on the top for the average of the data. That's another notation for it. So we can write that more formally as a sum. It's the sum, it's 1 over n times the sum from I from 1 to capital N of x sub I. So that's the mean. Then there's what's in English called the median. And this is the middle value if you write all the data values in a sequence. So if x1, x2, x3, all the way up to xn are written in ascending order, so we're just relabeling them so that x1 is the smallest value in the order, x2 is the next smallest, and so on. Then the median is the middle value. So if n is odd, it has a middle value. So for example, if n was 3, then x2 would be the middle value. So if n is odd, we can simply take the value x of n plus 1 over 2. So that's if n is odd. And people define it differently if n is even, but one way that is often defined is any value. So if we're even, we've got so if n were 4, then we would have x2 and x3 as sort of the two most central values, and they might not be the same. And normally any value, including those two values and between them, is counted as a possible median. So the median can be any value between x n over 2 and x n over 2 plus 1, if n is even. Okay, so that's the median. And the mode is simply the data value that occurs most frequently amongst all the data values. So the most commonly occurring value. But there may be more than one value that occurs most frequently, in which case the mode could be any of those. So it's the data value. Oops, I don't want that word to be up in the air like that. So let's put it down a bit. So the data value or values that occurs the most, occurs most often in x1 up to xn. Okay, so I'm sure you've met all these averages in school, these different notions of average. Maybe one thing that might not have been emphasized to you then, which I want to emphasize now, is one important difference between them is what kind of data they're applicable to. So in order to calculate a mean of data, we need to be able to add the data and divide it. And so that means this only makes sense for numerical data. So the mean only makes sense the median. However, to calculate the median, what we have to be able to do is write all the data values in ascending order. And in order to do that, we need an order on the data values. So the median makes sense for numerical data because we can order numerical data. We certainly have an order there, but it also makes sense for categorical data if it is ordinal data, if it is categorical data that we have an order on. For example, it would make sense to talk about the median opinion of the EU in our questionnaire about the EU, because there is an ordering on the opinions about the EU. So this makes sense so the median makes sense for numerical and ordinal data. And for the mode, we simply need to talk about the most common value, and that we can always ask what the most common value is, whatever kind of data we've got. So it makes sense for numerical ordinal and categorical data. But there is actually a little caveat here. That's I want to clarify things a little bit to say that in some sense, it's not really appropriate to apply the mode to continuous numerical data, because if your data if every data item is a real number, then it's always very unlikely that two different data items are going to be the same real number, because real numbers, they're continuous. You're never going to get exactly the same real number twice. If you look at the height of two people, for example, then however close they are in height, they won't be exactly the same height if one measures their height closely enough. So really, the mode it does make sense for numerical data, but it makes more sense for discrete numerical data than for continuous numerical data. Okay, so those are the three forms of average. So that's the measure of the central tendency, as I put, or the typical value of a set of data. The other thing I wanted to look at was the notion of spread. So let's look at measures of spread. And as I've told you already, we're going to look at just one of them, which is the standard deviation. Maybe standardny or clon or something like that. Is that right? Yeah. Measures of spread. So to understand the notion of measures of spread, let's consider how we might visualize data, so how we might present some data that we've gathered. So one of the ways that you probably learnt about this at school, or you'll have seen also in many presentations of statistics. So often we can picture the distribution of data using a picture called a chart. So often we can visualize the distribution of data using what's called a histogram, which is another word for something that's more simply called a bar chart. So an example of this would be, suppose we were looking at people's heights. So suppose we were looking at men's heights. Well, let's draw a little picture. So if we had men's height, so here we're going to have, whoops, so men's height. Oh dear, spelling height wrongly. And here we've done some survey of men, what their height is, and suppose we were asking them to answer to the centimeter. So this is in centimeters, and here we're going to have the frequency, so the number of people that gave a particular answer. And I don't know what the average men's height is. Maybe it's around sort of 1.75 m or something. I've got no idea. But wherever it's the average, we're going to have like typically more people. The average is typically going to coincide with, so let's say 175. The average is typically going to coincide, the mode is typically going to coincide with the mean, as it turns out, in such pictures. But anyway, there'll be more people than, there are likely to be more people than anything else on 175 itself, but not many fewer on 176 and 174, and not many fewer than that on 177 and 173. And anyway, I don't want to draw a very exhaustive picture, but at some point it's going to start dropping down a bit faster. And then we tend to get sort of very small people, but people can differ from the height by quite a lot. So I'll be sort of, I get some picture like that. So something like this. So this is the bar chart of, for every height, the number of people that, we've asked like 1,000 or 2,000 men to give their heights or something like that, and got these samples here. But when we've got a picture like this, it's kind of natural to smooth out the curve. It's a bit bumpy like this, but the non-smoothness is presumably rather a phenomenon that's got from the particular group of people we asked, if we asked a different group of people, we get a similar looking curve, but it wouldn't have exactly the same bumps in it. So it's natural to sort of smooth it out, and then we'd end up sort of getting a picture a bit like that. So when we abstract a graph of a function from such data, so the blue line is the graph of a function, we very often see, and there are mathematical reasons that we see this, which I won't go into, we very often see the same picture emerging, which is this particular shape of curve. We very often see, and it's called a bell-shaped curve because it looks like a bell. You know, a bell that you would ring, like a church bell or something. Or this curve is also called a Gaussian curve, after the mathematician Gauss, who we've talked about in other lectures on this course. So such a bell-shaped curve, let's draw it again, just without the histogram underneath. So a bell-shaped curve is going to sort of look like this in general. It's going to have a flat bit close to 0 and then a peak in the middle, and then come down again to it. It's supposed to be symmetric, but it's I've not drawn it very well, but anyway, we can imagine that it's symmetric. And in the middle, we've got the highest point, and this is the average. This is the average. This coincides with the average of the data. But as we go down this curve, we see that here it's getting, as we go down here, it's getting steeper and steeper, but at a certain point, the slope starts getting shallower and shallower. So a certain point around here, up to this point, as we go down, it's getting steeper and steeper, and then suddenly the slope gets shallower and shallower. So this is something that you've looked at already in the exercise classes. This is an inflection point. And the distance from the mean to the inflection point is a measure of how fat the curve is. So how widely spread the data is. So this is called, and this measurement is called sigma, and this is called the standard deviation here. So if we had, let's use maybe we'll use a green. So if we might also see a different distribution, a similar looking bell-shaped curve, but a steeper one like this, say. Now this would have the same average, but here I haven't drawn it so well, but here the point of inflection would be somewhere here. So let's maybe put this in pink. So for this curve, this would be a narrower. So here we would have a different, for the green curve, we would have a different standard deviation. That's the distance from the mean to this point of inflection. And what that's representing, so the larger standard deviation of the blue data is saying there are a higher proportion of the population has heights, if we're talking about people's heights, has heights that are quite a long way from the average. Whereas with the green curve, it's a narrower curve, and only a very small proportion of the population has heights that are a long way from the average. So the standard deviation is measuring, if we take some some typical, if we take some value of the population, how far is it likely to be from the actual average of the whole population? So there's a measure of the spread. We've got a large standard deviation, the orange one. So this is the standard deviation. I'll write that down in full of the green curve. And the orange one is the standard deviation of the blue curve. So this is the standard deviation of the blue curve. So the larger standard deviation means that values are more likely to be distant from the average. So data that exhibits this typical bell-shaped data, one often gets this shape or a shape close to it. And as I said, for good mathematical reasons. So data that exhibits this Gaussian bell shape it's a very important data, a very important kind of data because it often occurs. And so it's called, such data is called normally distributed, because that's the data, that's the kind of distribution we normally expect in many circumstances. We also say it has the Gaussian distribution. And it has the mean is the, as we saw, the value at which the bell-shaped curve takes its maximum. So that's the mean. We've seen the formula for the mean. And the other value, the distance from the mean to the point of inflection, is called the standard deviation. So standard deviation sigma. Whoops. So the notion of standard deviation doesn't just make sense for normally distributed data. You can use it for whatever numerical data you've got. So the notion is a measure of spread. It's always a measure of how typically distant data is from the average, from the mean, but we can define it for arbitrary data, for arbitrary numerical data. So the notion of standard deviation makes sense for arbitrary numerical data. And it's a very good and useful measure of spread. And it's defined by a particular formula, which looks a bit mysterious when you first see it. So it's defined by the formula sigma. Is what you do is you take the average of over all the data values from 1 to n, you take the average of the square of the distance from the data value to the mean. So you take the distance of the data value xi, we're summing x1 minus mu, x2 minus mu, and so on. And in each case, we take the distance from the mean and we square it. And we find the average of these square distances. And when we've done that, we take the square root of the whole thing. So we're taking the square distances, that makes you have the squaring, make sure we're only looking at positive values here, average them, and then take the square root. A mysterious formula, but it's very useful. And if we don't take the square root, then we also get an important quantity, which is also a measure of spread because it's just the square of the standard deviation. And this is also a very important property in probability theory and statistics, so it has its own name. So let me flag what that's called. The value sigma squared is also an important value of its own. It's called the variance. Okay, so that's the standard deviation. I should warn you that in statistics, you get another formula for standard deviation in which there's an n-1 here. And this is to do with subtle notions in statistics to do with whether you're taking a standard deviation of a population or a sample and exactly the circumstances in which you're doing that. So those are subtle points in statistics that we're not going to talk about further in today's lecture. It can be a bit confusing, but the main mathematical formula, the really important one to know for standard deviation, is this one, which has a 1 over n, not a 1 over n-1, just in case you've seen formulas with an n-1 there. Okay, so what I want to end with is just a little application of standard deviation to something a bit so not mathematical, but actually to physics. And this was something that, well, it's 10 years now since this happened, but it was big news at the time, 10 years ago when it happened, which was when the physicists discovered the final piece of the puzzle. They were physicists have been, ever trying to model reality, and they in the 1970s came up with something called the Standard Model, which seemed to take account of all the known particles that occur in the universe. But one of the particles in the Standard Model had not been actually found in nature. It's called the Higgs particle or the Higgs boson. And this was discovered only in 2012 an experiment by CERN, C-E-R-N, in Geneva, when they discovered in their Large Hadron Collider, they discovered finally the Higgs particle. So I just want to say how the standard deviation was involved in that. So application or use of SD, so standard deviation. So the background is in July 2012, so 10 years ago, physicists, so people doing physics, particle physicists at CERN, the European Atomic Research Agency, confirmed finally that they had discovered in their Large Hadron Collider that they had discovered the Higgs particle. And actually, this news had been brewing for a while, so it was everyone was quite excited about it because this was the missing piece in the Standard Model that had not yet been discovered. Every so often in the newspapers, we were told they're getting closer to a discovery, and eventually in July 2012 they announced a discovery. And what it meant to actually announce a discovery was that they were certain that the particle existed with a certainty. They actually quantify their certainty, how certain they are. Really, they're quantifying their uncertainty, but they're reducing their uncertainty, uncertainty with a certainty of how sure they are, with a certainty of 5 sigma. And what that means, sigma here means standard deviations. So the newspapers in 2012 were full of standard deviations. We were getting the news that they got up to 3.5 sigma, they got to 4 sigma, they got to 4.5 sigma, and then finally they got to 5 sigma, at which point the physicists are happy enough to announce that they've discovered a particle. So what this means is they work out what results they would expect from their experiment if the Higgs particle did not exist. So they draw a picture, so they work out theoretically, so if the Higgs particle did not exist, so then they're measuring some values. And if the Higgs particle did not exist, the results of their measurements, when they plot it, they get a summary result in the end, the sort of average of everything, and that forms a bell-shaped curve. So this is what they expect. So they're most likely to, if the Higgs particle didn't exist, they're most likely to observe a value around here. So here we have the mu, the mean, and here we have, so this is 1 sigma. I mean, standard deviation, we can say, well, let's normalize the results to just say this is 0. So if the Higgs particle didn't exist, they'd be most likely to get a value around here. You know, they could sort of pretty well get a value up to here and so on. Anyway, and so on. But actually, the observed result from their experiment is off this picture. Is greater than 5 sigma away from the mean, 5 standard deviations away from the mean. So this is, if the Higgs particle didn't exist, the expected results of the experiment would look like this. And actually what they observed is way off the picture of what's expected. It's so off the picture that if the Higgs particle didn't exist, then the probability of observing their result, so if the Higgs particle does not exist, then the probability of getting the observed result well, it's actually, as you can see, it's way off the picture. This curve is going to be very low. It's actually less than 1 in 3.5 million. So and this was in July 2012. Since then, this result, I mean, now it would be off the charts completely, the certainty with which. So they're saying, you know, the probability that our experiment was a fluke and it gave us this result with the Higgs particle not being involved is so small, we can neglect that as really, really unlikely, and we can conclude that the Higgs particle exists. So this is how physicists convince themselves that new particles exist, and they use the measurement of standard deviations as a way of quantifying that. So if you get 5 sigma away, then you have a new discovery. And right at the moment, so just to make it a bit more topical, the physicists at CERN are for the first time discovering some discrepancy in some particles, I don't remember quite what, that actually differs from the result predicted by the standard model. And at the moment, I think they're on around 4 sigma with this. But this is going to be the first, well, I think it's going to be the first result in physics that's really well confirmed when it gets to 5 sigma. That's going to show that there is some problem with the current model of particle physics, and it's not completely predicting the correct results for all interactions of particles. Anyway, I find this an interesting topic. I'm going to put a link to a video on the course webpage. You're welcome to have a look at this video. It's going to explain in a little bit more detail how this quantification of certainty in terms of multiples of standard deviation actually works. So let me just say, just add to this, watch the video linked on course page. Okay, so I'm going to get my controls back and stop sharing my screen, stop the recording.